Now that we understand energy, let's find a new way to transfer and transform that energy. Mechanical waves are waves that move through physical objects like water, string, or slinkies. A wave is an oscillation or vibration that's accompanied by a transfer of energy that travels through space or mass. That space or mass that the energy travels through is called the medium. A medium is an intervening substance, such as air or water, through which a wave can transfer its energy. Right now, you're hearing me. Those are sound waves traveling through air. So even though the sound energy is being transferred, the medium, in this case the air, doesn't move along the path. Waves transfer energy. The medium does not move with the wave. Let's use this wave pool as an example. As the wave moves through, the medium is the water. You can see the people floating on the medium, but you'll notice that after that energy passes through, they end up relatively in the same place. They were displaced when the energy transferred through them, when the energy transferred through the medium of the water, but they themselves did not move with the wave. They went right back to where they started. This water wave is an example of a transverse wave. Transverse waves is a wave that vibrates perpendicular to the direction it's traveling. So in this example, the wave is moving to the right, the energy is moving to the right, but the mechanism, the red block, is moving up and down. It's causing the vibrations perpendicular to the direction of the wave. Light and water waves travel as transverse waves. There's some terminology to understand with transverse waves. Equilibrium, this is the midline of the wave. This is the medium of the wave's resting position. If I put no energy in, it's at equilibrium. The crest is the highest point on a wave. The trough is the lowest point on the wave. A wavelength, this is the distance between successive crests of a wave. So you can measure this crest to crest, trough to trough, or a wavelength includes one full crest, one full trough. The amplitude of the wave is the distance between a crest or trough and the equilibrium. It's based on the amount of energy in the wave. If there's more energy, it's a bigger amplitude. If there's less energy, it's a smaller amplitude. It's further away from that equilibrium. Let's put those terms into our diagram. Here's our equilibrium line. This would be if the string had no energy. The crests are the highest points. The troughs are the lowest points. When we measure the distance from the equilibrium, from that midline up to a crest or down to a trough, this is the amplitude. It's based on how much energy. And that makes sense if I'm moving the hand up and down to move this string. If I move it higher, I'm putting more energy in, so I have a higher amplitude. If I don't move it as high up and down, I have less energy. I have smaller amplitudes. These are our wavelength. A wavelength is from a crest to a crest, a trough to a trough, or it's one full wave is one crest, one trough. Let's figure out how we find the number of waves. So in this case, we have a wave pattern. That's one wave, from a crest to a crest, crest to a crest, crest to a crest, and then we're left with one half wave. You can also think of it as trough to trough, trough to trough, trough to trough, and we're still left with 3 total waves and a half of a wave. You can also look at it as one trough, one crest, one trough, one crest, one trough, one crest. In this case, we're left with a quarter of a wave on each side, so we still have 3 full waves and a half of a wave. A longitudinal wave or compressional wave is a wave caused by vibrating in the same direction as the waves traveling. You'll notice the waves are moving forward because the mechanism, the red block, is going backwards and forwards. It's creating areas where the molecules of air, in this case, are compressed or they're separated. Sound waves travel in this pattern very commonly. So we have an example of a tuning fork here where the tines vibrate. They compress air back and forth. They're acting like an accordion, pushing that air back and forth. There's some important parts to look at in a longitudinal wave. The compression is a region in a longitudinal wave where the particles are closest together. They're compressed, they're pushed together. A rarefaction, so not a rare fraction, but a rarefaction, is a region in a longitudinal wave where the particles are furthest apart. So we compress, the mechanism pulls back, and that creates a rarefaction. Now they're separated, they're further apart. The wavelength is the distance between two consecutive compressions or two consecutive rarefactions. Let's put those terms on a diagram. We have areas where the waves are compressed, areas where the waves are separated. Compressions are compressed, rarefactions are separated. We can measure our wavelength by looking or measuring from the end of a compression to an end of a compression. Just like a transverse wave includes one full crest and one full trough, a full longitudinal wave involves one rarefaction and one compression.